These are the frequently asked questions for Algebra 2 for section 7.4. And I'm going to start here with number 17, which has been totally broken apart and expanded. And we have to think about how to put all of that back together. And you can see that these all have the same base. It's all logarithm base 3. So we try to figure out, what is addition, and in some of the cases we see up here subtraction. What is that doing? So in number 17, everything that we see there is addition, and addition means multiplication. So this is really the logarithm base 3 of 4 times y times 8x, because again, when we're talking about the language of logarithms, we are talking about the language of powers. And in power language, when you need to multiply, you add. So this is multiplication. So this would be the logarithm base 3 of 32 xy. And you just pull all of that together. Now, let's see, in this group, I want to do one more, and I'm trying to figure out what would be a good one. Let me look at number 13 with you here. So number 13 isn't just the addition. That's the reason I'm choosing that one. And I noticed that I have a 4 out in front, and that's multiplication. So I think, okay, power language, what are you doing when you're multiplying? You're raising a power to a power. So what I need to do is put that 4 back up as a power for the m. And then it's minus the log of n. So now that power is back up where it belongs, and now I have subtraction. So I think, well, where does subtraction come when you're talking about the properties of exponents? And that comes from division. So this will be the logarithm of m to the 4th over n. So again, just a couple of different examples there. Hopefully these aren't messing with you too much, but you think about those properties of exponents that we have and use those with logarithms. Then number 24, 26, and 28 say expand each logarithm. So number 24, we have the logarithm base 3 of 7 times 2x minus 3, that quantity squared. So the first thing that we see here is that there's definitely some multiplication. So let's pull that apart, because we have the logarithm base 3 of 7 times 2x minus 3 squared. We would want to use addition to rewrite that. All right, and now that I have that multiplication separated, I can see in the back that I have a power. And that power needs to become multiplication. Now, here's where people will get a little confused. As you're looking at that back portion of the logarithm there, that 2x minus 3, some people, will say, hey, let's keep going with this. But we can't, and that's because notice there are parentheses there. That's meant to be kept together. So we can put the power out in front, but what we can't do is break apart that 2x minus 3. That's all part of one quantity right there. Then, in number 26, well, the smart part doesn't want to work for erasing right now. So 26, we have the logarithm base 4 of 5 square roots of x. So we see the multiplication. That means we have to change that to addition. So logarithm base 4 of 5 plus logarithm base 4 of the square root of x. Then we can't leave radicals in here. We have to change those to fraction powers. So logarithm base 4 of 5 plus logarithm base 4 of x to the 1/2, because the square root is the same thing as raising it to the 1/2 power. And then finally, we have to bring that power out in front and make it multiplication, because when you raise a power to a power, you multiply. And we have undone everything that we can undo at this point. So changing the multiplication into addition, changing our radical into a fraction power, and then using that power to a power property to bring that out in front and multiply. Number 28. Number 28 has the logarithm base 5 of 25 over x. So pretty obviously that's division. And in logarithm language, we don't divide, we subtract. Oops. Got started thinking about the answer here and was writing things that I shouldn't write. There we go. So we have logarithm base 5 of 25 minus logarithm base 5 of x. Now, why did I start thinking ahead about this first piece? Because we know what that is. That's 2. Snail shell that in your head. 5 to the something is 25. Logarithm base 5 of 25 is going to be 2. Now, you could also write it this way so that you can see those inverses. Write 25 as 5 squared. These drop out and we get 2 minus logarithm base 5 of x. That is one of the very cool things that happens with logarithms when we're using those. Number 30 says use the change of base formula to evaluate each expression. We have logarithm base 2 of 9, and in this case we would use the logarithm of 9 divided by the logarithm of 2 so that we could go ahead and punch that into our calculator. We just use that common base of 10 for the common logarithm for both of these. So we need logarithm of 9 divided by the logarithm of 2. All right, there we go. Generally, we go 4 decimal places on these. So we have 3.169925, so it'll be 3.1699 for our logarithm answer. So that's that change of base formula we talked about in class, where when we need an answer and we do not have a calculator available that allows us to change the bases, we use this formula to get it. And that's really important that you know that one. You forget your calculator, you have to use what's available, you have to know what you can do. Then number 43 says use the properties of logarithms to evaluate each expression. Now these are a lot of fun because with these what we're trying to do is we're trying to get an answer. We're trying to get a number that we can use here. So with 43 we have the logarithm base 4 of 48 minus 1/2 the logarithm base 4 of 9. And that 1/2 got my attention because that's supposed to be a power, and it's a power of 1/2, which means it's a radical, which is the square root of 9. So this is the logarithm base 4 of 48 minus the logarithm base 4 of 3. And now I see that there's subtraction, and subtraction comes from division. So this is the logarithm base 4 of 48 divided by 3. So it's a logarithm base 4 of 48 divided by 3, which just happens to be 16. And then we can either snail shell this in our heads and say, hey, it's a 2, 4 to the something. Remember, we put an equals x over here. We snail shell this. 4 to the something is 16. That something is 2, and that's our answer. Or we can write this as the logarithm base 4 of 4 squared. And of course, those are inverses. And we still get 2 for our answer. Either one of those ways is an acceptable way to do this. I like the snail shelling because it starts to get you thinking about how logarithms work, getting you to translate logarithms into your head just as you would if you were learning a second language. Then, number 44. 44 is a very cool problem. So let's take a look at 44. 44, we have 1/2 logarithm base 5 of 15 minus logarithm base 5 of the square root of 75. All right, so many different things and ways that we can do this problem. So I'm going to take my 1/2 power and rewrite that as the square root of 15, because this would go right back up here, and that of course is the square root of 15. Now, I look at this one and I think I have subtraction here, and subtraction is division, and they're both square roots, so I should certainly go ahead and see what the square root of 15 over the square root of 75 is, and that will actually reduce, if we think of that as one fraction here. We've got the 15 over the 75, and that's 1/5. So this is the logarithm base 5 of the square root of 1/5. Now, I get to thinking about the base of this logarithm. It's a 5. So if I can get the square root of 1/5 to be represented as 5 to some power, then everything's going to drop out, and I'll just be left with the power as my answer. So let's start here by saying, okay, we know that 1/5 is 5 to the negative 1. Then we know that square roots are the 1/2 power. So this is really logarithm base 5 of 5 to the negative 1/2, because when you have a power to a power, you multiply. And that is where it gets really cool, because these two are going to drop out. They are inverses of each other, and we get a negative 1/2. So again, you need to go back up here and take a look at this and realize that this is a very, very fancy mathematical way to write negative 1/2. That is cool. All right, then 56, write each logarithmic expression as a single logarithm. So we're condensing here. And we see these 1/4s. And hopefully you're saying to yourself, hey, that's in both of them. So, you know, kind of silly that they did it for both, but we'll go ahead and put them back up as powers. The logarithm base 3 of 2 to the 1/4 plus the logarithm base 3 of x to the 1/4. And then we see that we have addition, and addition is multiplication, so it's logarithm base 3 of 2 to the 1/4 and x to the 1/4. Well, they're both to the 1/4 power, which means they were both 4th roots. So we can go ahead and put them back underneath that 4th root symbol. And now we have everything as it would be if this were a problem that said expand. So we're using this forwards and backwards process, the inverse process, to get these written. Then, number 57. Order of operations has always told us to do what's in the parentheses first, so we are going to do that. We see that there's addition inside with those logarithms, so what we have to do is we have to multiply. So that'll be the logarithm base x of 4y minus 3 logarithm base x of z. Now, what I would do next is put those powers back up where they belong. So logarithm base x of 4y to the 1/2 minus logarithm base x of z to the 3rd. Now, I notice I have a 1/2 power up there. And inside that 1/2 power, I have a 4, which is a perfect square. So I would take a second and say, you know what, that's the square root of 4y, to just get myself all settled in on what I have going on there. And the square root of 4 is going to be 2, so this is logarithm base x of 2 square roots of y minus logarithm of base x z to the 3rd. So now, last but not least, we have some subtraction to deal with, and subtraction is division. So this is logarithm base x of 2 square roots of y, and that's going to be divided by z to the 3rd. So logarithm base x of all of this, I'm going to put parentheses around that so there wouldn't be any misunderstanding about what we have over there. Logarithm base x of the quantity, 2 square roots of y over z to the 3rd. Number 60, expand each logarithm. So in number 60, I see that all of those terms are underneath that square root symbol. And that's the same as a 1/2 power. So I'm going to say this is logarithm of the quantity 2x over y to the 1/2 power. Now I'll bring that 1/2 out in front, because when you raise a power to a power, you multiply. So that 1/2 comes out into the front. And now I realize, well, all of them need that 1/2. So I'm going to have to be careful as I go through this to use parentheses so that I have a 1/2 with everything. Because what I see here is multiplication, which means addition, and what I see here is division, which means subtraction. So this is 1/2 times, we have the logarithm of 2 plus the logarithm of x, that takes care of our multiplication, minus the logarithm of y. And again, those parentheses are important because every single one of these needed that. Now that would be an appropriate way to write the answer to this problem. You also could distribute that 1/2 to every term here, like so. So we want to expand it. That means we really should try to get rid of parentheses as much as possible. And we definitely can, because that's multiplication. Now multiply that times everything that we see, which would be every term. Then number 61, logarithm s square roots of 7 over t squared. Well, what most people are going to see right away is the division. So logarithm of s square roots of 7 minus logarithm of t squared. Now, hopefully you see the powers. This is the logarithm of s, and we have 7 to the 1/2 minus the logarithm of t squared. So, I notice the s does not get the 1/2 power. We can see that right up here at the beginning. So that means we have to separate the multiplication first before we put those powers forward, like we talked about in class. So the logarithm of s minus the logarithm of 7 to the 1/2 minus the logarithm of t squared. And now I can bring those powers out in front of each term as multiplication. So we have logarithm of s minus 1/2 logarithm of 7 minus 2 logarithm of t. And now that's been expanded as far as it can possibly be expanded. I put a minus there instead of a plus. So this, our multiplication, is addition, and then our division is subtraction. All right, where else? Just wanted to do that last one with you, number 63 up there. So, let me erase these and make a little bit of room. All right, 63. This problem, it's kind of bad form, but what we want to do is expand this so that somebody could get back to the original if we gave them our expansion. Because first of all, that p to the -2, we know that isn't simplified. That should really be moved up to the top. However, your book wants you to see a process here, so I'm going to go through that process. What we have is, we have division, which of course is going to be subtraction, and then we have multiplication, which is addition, but we have two terms down there in the bottom. So we're going to need to separate that division first by using subtraction and parentheses. And that's because that logarithm of m cubed is being divided by both the n to the 4th and the p to the -2. So we have subtraction here to cover this division, and then we have addition right here to cover that multiplication. Now, inside those parentheses, we have some powers, so let's bring those down. That'll be 4 logarithm of n minus 2 logarithm of p. And in the front, we can bring that power out. Now, as you take a look at the back portion of this, you're going to notice we have a negative out in front of parentheses. And of course, we should distribute that. So that'll be minus 4 logarithm of n plus 2 logarithm of p. And now we wouldn't have any parentheses as we go through that problem. So the book wanted you to see that you absolutely can distribute this negative, through those parentheses, just like you normally would. But like I said, this is really bad form because we know that that's not simplified and it really should be moved up to the top. However, they want you to see that distributing a negative works just fine with logarithms. That's it.